Welcome to this module, and this module is in continuation with our last module on which we were looking at fabricating a biochip that is integrated with 3 different sensors, and these 3 different sensors would be used to understand the change in the tissue properties. So, when I say change in the tissue properties, I mean a stiffness of tissue, that is its mechanical property, the resistance of the tissue, that is its electrical property, and the thermal conductivity of tissue. So, we are looking at 3 different points: mechanical, electrical and thermal. In the last module, what we have seen is that how we can fabricate a micro heater, on that how we can deposit a silicon dioxide and create a window, and that process flow we have seen, right. In this class, this module, what we will look at, we will be concentrating on how we can further work on interdigitated electrodes followed by other sensing layers. So, that finally we have a biochip. So, if you remember and if you see on the screen, the last slide, right, of the last module was to show that we now have this particular one, okay, this one, my magnetics, this one. So, you have in micro heater, on that there is a silicon dioxide which is an insulator, and the contact area of the micro heater is opened. The contact area of the micro heater is open. You can see here contact area, right. The silicon dioxide is removed from this contact area. Now, what to do? Now, what to do? So, we will see now how to create an interdigitated electrodes. So, let me draw the last section of the last slide of the last module, and that is I have a silicon wafer with silicon dioxide, right, that is called oxidized silicon wafer. Okay. If there is a SiO2 on silicon, it is called oxidized silicon wafer. On this oxidized silicon wafer, I was having a micro heater like this, and then this micro heater was protected by a insulating material, right, and this insulator is also silicon dioxide. This insulator is silicon dioxide, and you can see here the contact areas are opened. Contact area is opened, silicon dioxide, and this is your micro heater, or we can say the material nichrome. All right. What is the next step? Next step would be we take this oxidized silicon wafer, and on this oxidized silicon wafer where you have the micro heater, correct. And you have your contact area open, right. On this I will deposit a metal which can be my chrome gold. This metal will be used for patterning interdigitated electrodes, right. This is SiO2. SiO2 again, because oxidized silicon wafer, and this is my nichrome, correct. So, we have a heater on which we have deposited chrome gold. Chrome gold will be used for fabricating interdigitated electrodes. What is the next step? Next step we all know, right. What is that? We have to spin coat. A photoresist, right. We have to spin coat a photoresist. So, this is my positive photoresist, I have spin coated it, alright. Next step will be soft baking or pre-baking. Soft baking or pre-baking, we know it is 90 degree centigrade 1 minute on hot plate, right. After this, next step would be I will load my mask, right. I have to load my mask. So, we have oxidized silicon substrate, always this is your process flow, okay guys, this is your process flow, and we have heater 1, 2, 3, 4, let us draw it correctly, it does not look perfect, 1, 2, 3, 4, 5, and then we have SiO2 covering the heater. Right. On that we have chrome gold, on that we have photoresist. Let me just draw a little bit thinner silicon dioxide, so that we have enough space. On that we have chrome gold, on that we have photoresist, sorry about this, we have photoresist, right. So, let us draw photoresist, on that we have to load mask, a mask. So, what should be my mask? My mask should be bright field mask, my brush would be bright field mask, right, because I want to save my chrome gold in this particular area to form my interdigitated electrodes, all right. This is what my bright field mask, let me write it down like this, bright field mask. What is this? This is my photoresist, right, photoresist which is soft baked, positive photoresist. Then what is this one? This is my chrome gold, right. What are these things? These are my silicon dioxide, sorry, and we know what is this? Nichrome. And what is this? Silicon dioxide. What is this one? Silicon. What is this one? Silicon dioxide, correct. What is this? Bright field mask. After soft bake we can load a bright field mask, right. Next is I will expose, I will use UV light to expose the above wafer. When I perform UV exposure, what will happen? The area which is not exposed, by UV light, right, will be stronger. Why? Because we are using positive photoresist, right. So, after UV expose I will develop this wafer in photoresist developer. I will develop this wafer in a photoresist developer. When I perform photoresist developing, Then after photoresist is developed, what I will have? After photoresist is developed, so this is my photoresist, then this is my chrome gold, then this is my SiO2, this is my nichrome, right, this is SiO2, silicon, SiO2, correct. This is what I will get after I perform my photolithography. After this, the next step is that I will next step. So, I will just draw a line like this. The next step would be I will etch my chrome and gold, right, my metal to form interdigited electrode. So, how can I etch? I will dip this wafer in chrome etchant, followed in first gold etchant, followed by chrome etchant, gold etchant followed by chrome etchant, right. So, it is a wet etching process, right. So, what will happen? The photoresist will be stronger and it will stay as it is. The photoresist where it is protecting the chrome gold, right, will stay as it is. But see, after you develop photoresist, one step, did you forgot one step after developing photoresist? After developing photoresist, the next step can be, or next step should be hard bake, right, hard bake, and hard bake is done at 120 degree 1 minute on hot plate, correct, hard bake. Then we will do wet etching, okay. Then we will remove chrome gold. So, now when we remove chrome gold, we should know that we have this heater on which there is a silicon dioxide, right. We have this heater covered by silicon dioxide, and then when we perform this etching, what we will see? We will see what etching we are performing? We are performing wet etching, wet chemical etching for removing chrome gold. So, what is this? This is your photoresist, right, and this material, right. So, how we have written chrome gold? We have shown chrome gold by wavy line, right. We will draw wavy line everywhere, so that we know what is chrome gold. So, here you see this is my wavy line chrome gold, right, and over chrome gold I have photoresist. This is my chrome gold. Now, the next step would be acetone dip. When I dip the wafer in acetone, what will I have? I will have a beautiful oxidized silicon wafer on which there is a micro heater. There is a micro heater. Let us draw. Micro heater on which there are interdigitated electrodes. These are interdigitated electrodes, right, and this is your silicon dioxide, as you know now. So, what we have now? What we have? We have silicon, we have silicon dioxide, we have silicon dioxide once again for here, right. This is a protective silicon dioxide, then we have here nichrome which is your micro heater, and on the top of nichrome we have interdigitated electrodes made up of chrome and gold. Got it. So, if we repeat quickly, what is that? You take this wafer where there is a micro heater and the contacts of the micro heater are open, on that you deposit chrome gold, followed by spin coating photoresist which is a positive photoresist, followed by soft bake which is done in 90 degree 1 minute, followed by loading the mask and UV exposure, then you have a bright field mask. So, the unexposed area, because there is a positive photoresist, will be stronger and the exposed area would be weaker. So, after UV exposure you can see that the area which were not exposed got stronger, and this is the pattern that you get. After this you have to perform a hard bake which is 120 degree 1 minute, followed by etching the chrome and gold. First we have to dip in gold etchant, followed by rinsing the wafer. Rinsing is in using the DI, and then you have to dip the wafer in the chrome etchant, and again you have to perform a rinse, DI rinse. After that you have to put this wafer in a acetone to strip off the photoresist. We do not require photoresist. When you strip off the photoresist with the help of acetone, you obtain a wafer which has now a bottom layer which is a micro heater. On this there is an insulator, on which there is an interdigitated electrodes, and this layer looks like the one that you can see in front of your screen. Right. What is this? There is a micro heater at the bottom. If you see this one, right, there is a micro heater at the bottom, and then on that micro heater there is an insulator which of course you cannot see, because silicon dioxide is a transparent material. This is an SEM image, right. So, the bottom, if you see, these are the contact to the micro heater. These are the contact to the micro heater, and then there is an insulator on which there are interdigitated electrodes, and you can see here that there are 1, 2, 3 and 4. Right, 1, 2, 3 and 4 interdigitated electrodes. That is why we need 8 contacts, 1, 2, 3, 4, 5, 6, 7 and 8. And you can see there is one more gold electrode that we will see that why we are using that electrode. But until here it should be completely clear to you what we have done. You can see this image as well, where you can see a micro heater at the bottom, right, in a coil structure, rectangular coil or rectangular fashion, on which there is an insulator, on which there are interdigitated electrodes. These are interdigitated electrodes, right, 1, 2, 3, 4, correct. So, this is where we obtain our interdigitated electrodes. Now, the next step would be how to deposit and pattern piezoresistive material, right. On this we require a piezoresistive material, because our ultimate goal is to use this as a sensor to measure the stiffness of the tissue, right. How to deposit piezoresistive material, and then how to perform photolithography, so that we can obtain a sensor, a biochip with a heater and a piezoresistive material, right. So, we will see the lithography technique in the next module, where we will deposit a piezoresistive material on this particular wafer, and then once we deposit using a PVD, which is physical vapor deposition, piezoresistive material, then we will perform lithography. After that we have to perform a third step, which is your insulator on piezoresistor, on which there is an gold pad which will act as an electrical sensor, and on that gold pad again we are using SU8 pillars which will make it conductive. So, if you see it looks very easy when you say that biochip indicated with mechanical sensors, electrical sensors and thermal sensors, but when you fabricate it, it has multiple steps. But again, once you know photolithography, or once you know the process flow and a recipe, you can create many complicated devices, and one such device we are talking about in this particular series of modules. All right. So, in the next module we will see how we can finish the biochip fabrication. Till then you just look at the today's lecture, look at what we have discussed, see how we can obtain interdigitated electrodes, what are the methods that I have talked, which is particularly a lithography technique, right. Till then you take care, I will see you in next module.